Hello everyone, let's try to be a cheat code ninja today. Even though this problem is marked as a hard problem, I would say that it is similar in difficulty levels to a medium problem. Let's look at it. We are given a complete binary tree of n levels. So each row in the tree except the ones in the last level have two children. The left child's value is 2 into the value of the node. For example, you can see that the value of the left node is double the parent node. And the right child value is 2 into the parent's value plus 1. For example, you can see that the right child's value is 2 into 1 plus 1. Similarly, over here, the right child's value is 1 more than the twice of the parent value. We are also given a queries array containing the values of two nodes. We have to add an edge between those two nodes and find the length of the cycle formed. It is given that the length of a cycle is the number of edges in that cycle. Let's look at the example given. The first query has the nodes 5 and 3. So we'll connect those two nodes using an edge, and the cycle formed between them will contain these 4 edges. The second query has the nodes 4 and 7. We'll connect those two nodes using an edge, and the cycle formed will have these 5 edges. Our third query has the nodes 2 and 3. So we'll connect them using an edge, and the cycle formed will have these 3 edges. Let's try to come up with an intuitive solution for this. Let's try to understand more about this problem using this example. Let's say in our query we are given these two nodes. When we connect them to form a cycle, it will be of length 3. And let's say if we have these two nodes, then if we form a cycle, it will be of length 4. But what happens if we have these two nodes given in the query? Firstly, we'll connect both these nodes, and the cycle formed will be this. One thing to note over here is that this will be the node from which the edges of the cycle will start, and the root of the whole binary tree will not be part of this cycle. Similarly, for these two nodes, the edges of the cycle will be, so our cycle will start at this node. Any node which is above it will not be included. And for calculating the length of the cycle, the number of edges between 2 and 8 is 2. The number of edges between 2 and 5 will be 1. And we'll have one extra edge for connecting the query nodes. So the length of the cycle will be 4. Similarly, for these two nodes, the number of edges required to form a cycle will be 5. Let's see if we can derive a formula for this. If we take the start of the cycle, the number of edges between 1 and 4 will be the difference of the levels between them. As you can see, the number of edges will be 2. And similarly, the number of edges between 1 and 7 will also be 2. We'll also need one extra edge to connect 4 and 7. So in total, we'll need 5 edges. So once we find the node which starts the cycle, we can find the length of the cycle that will be formed. And if we notice carefully, this node will be the lowest common ancestor of our query nodes. So for any two query nodes, we first have to find their lowest common ancestor. And once we have that, we have to find the number of edges between it and the query nodes. We'll also need an extra edge for connecting the two nodes. So the length of the cycle will be the sum of these 3. So the problem we have is how do we find the lowest common ancestor of two nodes? If we take these two nodes, all the ancestors of 13 will be, and similarly all the ancestors of 4 will be. In this case, node 1 will be the first node where their ancestors intersect. So this will be the lowest common ancestor. Each node can have n ancestors, so we can store these ancestors in a hash set and find the intersection between them and take the maximum of it. Let's see how we can optimize this. Rather than storing all the ancestors, let's try to store just one ancestor for the queries, and whenever we find that both of them are the same, that will be our lowest common ancestor. Let's see some problems associated with this simple approach. The ancestor of 4 will be 2 and 11 will be 5. Both of them don't match, so we'll repeat this process. The ancestor of 2 is 1 and 5 is 2. Ideally, they should have intersected at node 2, but if we continue like this will never happen. So obviously this won't work. This is because from the lowest common ancestor, node 4 is just one step below it, while node 11 is two steps below it. So it will take two steps to reach node 2 from node 11. But if we go two steps above from node 4, we'll reach node 1. So if somehow both of these nodes were at the same level, they will reach the lowest common ancestor at the same time. So it would make sense to move node 11 first so that both of them will be at the same level. To determine which node should move first, we can check whichever is greater, we'll move it first. For example, 11 is greater than 4. So our pointer will move from node 11 to node 5. And now again 5 is greater than 4. So we'll move pointer 5 by one step to bring it at 2. So now 4 is greater than 2. So we'll move its pointer by one step and now it will be at 2. Finally, they have arrived at the same node. That means we have reached our lowest common ancestor. Let's see this again in action for this small example. As 5 is greater than 4, we'll move it to its parent. And now we'll move 4 to its parent. We see that both of them point to the same node, hence that is the lowest common ancestor. This will even work for the case when one of them is itself the lowest common ancestor. We'll move two steps above from node 8. Node 2 is already the lowest common ancestor, so we'll move 0 steps. It is given in the question that there can be multiple edges between the nodes. So there will be one edge between 2 and 8. The answer is 3. Let's see how we can simplify the calculation of the number of edges. Initially, we'll move one edge up from node 15. We'll add it to our answer. Now we'll move one edge up from node 8 and we'll add it to our answer. Similarly, we'll move up from node 7 and add it to our answer. Now we'll move up from node 4. Now we'll move up from node 3. And now we'll move up from node 2. Now we have arrived at the lowest common ancestor. We'll need one more edge to connect these two nodes. So this will be our answer. The time complexity of this would be, for each query we have two nodes, and for each node we have to travel up to reach the lowest common ancestor. This would take log n time. So in total this would be q into log a plus log b. And for the space complexity, if we ignore the array required to store the output, our space complexity would be constant because we are only maintaining pointers to the two nodes. Let's implement our solution. Let's define an array to store our output. Now we'll go through both the nodes of each query. We'll require one edge to connect them. Now we have to find their lowest common ancestors. We'll repeat this process until both of them are the same. For the larger of these two, we'll move to the parent. Hence we'll divide it by 2. So their new values will be the minimum of them because it did not move and the parent of the larger one. As we have moved one edge up, we'll increment the count of the number of edges we have seen. And once we have arrived at the lowest common ancestor, we'll append this to our answer. And once we have gone through all the queries, we can return our answer. Let's submit our solution. You can see that our solution is accepted. If you have any doubts or concerns regarding this solution, please mention in the comments. If you thought this video was helpful, please leave a like and subscribe to the channel for more such content. Thanks for watching.